We're going to describe and do an example using the Swedish Slip Circle Method. In this method, there are various assumptions. The first one is that the failure surface is circular. So we can, for example, take a circular object right here and draw a circle, and by doing so we have created a wedge with a circular failure surface. Right? This is the wedge right here. Number two, notice that any normal force that acts on the failure surface, obviously perpendicular to it, passes through the center of the circle. This makes things easy, let's say, in terms of calculations. This particular case is relevant for undrained conditions. So, essentially, the strength that is relevant is the undrained strength. And one important aspect of this is that the strength is assumed to be not a function of the stress that acts at the point in question. So for example, you have a point here, obviously the strength is the tau that can be sustained there, the maximum tau that can be sustained, and there is a sigma here. We're saying that this S is independent of that sigma. And therefore, if this is, let's say, one soil, then the S here and the S here are all the same. Because the strength is undrained, we're basically saying that we are adapting this method to cases where the soil is saturated. The saturation is 100%, right? Clearly, when you have an undrained case, you're essentially talking about fine-grained soil, particularly clay. Okay, so we're going to say mostly clays. Okay, here's an example. Right here we have the ground surface. It's broken into two slopes. There's another dark line here that denotes an interface between a layer above and a layer below that line. And our failure surface is described by this circle that has a center right here. And you can see that this is the failure surface right here. We're going to say for simplicity, and well, as an example, that the grid here is 1 meter by 1 meter. For all this to work, clearly the slope has to be drawn to scale. Okay, so let's say that this is 1 meter in our example. The topsoil layer, which is up here, has an undrained strength of 100 kPa, and the one down here has an undrained strength of 80 kPa. The unit weight of this layer here is 20 kilonewton per meter cubed, and the unit weight of this one is 22 kilonewton per meter cubed. So we proceed as follows. We have to divide this wedge into slices. The first thing we do is the following. We take our finger or our pencil, we walk essentially along the ground surface. Okay? Every time we see a break in slope, we draw a vertical line. Right here, we continue, break in slope. We continue, and there's a break in slope over here, but this is outside the circle, so we don't have to draw a vertical line there. The next step is to take our pencil again and walk along the failure surface. Every time we see a change from one layer to another, we draw a vertical line. So we keep going. Right here, there's a change, right? From layer 1 to layer 2. So we draw a vertical line. Keep going, we keep going. We're in layer 2, we're in layer 2. Right here, we switch from being in layer 2 to layer 1. Therefore, right here, there's a vertical line. Actually, it should be drawn like this so that we can cut the wedge into slices. You can see that that is happening. There's one here, another one there, another one there, another one there, etc. But this one is going to actually be cut a little more. All right, last line to draw is a line right under the center of the circle. Okay, so now we have created 1, 2, 3, 4, 5, 6 slices. 1, 2, 3, 4. This fourth one is a very narrow one, right? Let's say relatively. It's 5 and 6. 6 slices. So what I've done here is I've redrawn the cuts, right? The vertical lines in red, and I have put numbers here on the slices. 1, 2, 3, 4, 5, and 6. The next step is to determine the area of each of these slices. And given the fact that we have straight lines and a curved line, we're going to essentially make approximations of these areas. Clearly, when you use a computer, the computer's approximations are of much higher resolution, and therefore it can actually calculate areas quite closely to what they truly are. In our case, by hand, we're going to approximate. Slice number 1 looks like a triangle, even though the hypotenuse is curved. But we can approximate the area utilizing trigonometry, or geometry, sorry. All right, so how big is this triangle? Well, remember that this element is 1 by 1. So we could say that this triangle has an area of 1/2 base times height. The base is 1.5 and the height is 1. We're going to take that area and multiply it by the unit weight of this soil. The unit weight of this soil is 20 kilonewton per meter cubed. So area times unit weight is, in this case, let's see, 20 divided by 2 is 10 times 1.5 is 15 kilonewton per meter. So what is this? Let's pay attention closely. Because the length into the page is larger than the nominal size in this direction or this direction of the slope, then we can treat this slope as a two-dimensional problem, which means that we take 1 meter of slope into the page and analyze it. So we say that the weight of the slice is 15 kilonewtons per meter of slice into the page. Slice number 2 is composed of 2 types of soil, soil 1 and soil 2 down here. So we're going to incorporate that. All right, so what do we have? We have here a rectangle. The rectangle has an area of 2 times 1. And the unit weight is 20. And the triangle has an area of 1/2 base times height. And its unit weight, that is of soil number 2 down here, is 22, right? Kilonewton per meter cubed. So this is 62 kilonewtons per meter. Number 3. Number 3 has also 2 components, one on top of the other, meaning 2 soils. So let's look at this triangle first. 1/2, 1.4 times 2, that's this part. All that times 20 kilonewton per meter cubed, that's this part. Then we have 1.4 times 1 times 20, that's this part. And then we have this bottom part here, which is also I mean, we're missing this little piece here, but we could say 1.4 times 1 times 22, which is 86.8 kilonewton per meter. Number 4, 0.6, right? If this is 0.4, then this is 0.6. I apologize, this wasn't on the screen, so let me just tell you what I did here. First, I calculated the area of these 3 little blocks here. So 0.6, which is this, times 3, that's that rectangle, times 20 kilonewton per meter cubed. Then the little triangle up here, 1/2 base times height. 1/2 base, 0.6 times height, 1 times 20 kilonewton per meter cubed. And then this bottom part here, which is 0.6 times 1 times 22 kilonewton per meter cubed. 55.2. Number 5. What do we have here? We have this big rectangle, 3 times 4 times 20 kilonewton per meter cubed. That's all that, right? This triangle, 3 times 1 times 1/2. And then this triangle down here, which we are going to say also that is 3 times 1 times 1/2 times the 22 kilonewton per meter cubed. This is 303 kilonewton per meter cubed, or kilonewton per meter, sorry. And then number 6. Let's do it on the side here. Okay, so what do we have here? One thing that I think that you could do also, I mean, this is kind of more rustic, let's say, or more rough. But the idea is that you can simply count the number of squares, right? And approximate, obviously, because we're doing this by hand. So we could say, look, we could say that these 2 make 1. These 2 make 1. So 1. These 2, if I put this one up here, that makes 1. So 2. 3, 4, 5, 6, 7, 8, 9, 10. Right? 11. Each of these is about 2/3, right? So we have 11 plus 3 2/3, right? Which is 2. And then we have this little piece right here, which is about maybe like 1/10 of 1, right? So we have here 11 plus 2 plus 1/10, which is 13.1, right? All that times soil 1, which is 20, which is 262 kilonewton per meter into the page. Right, so 1. Oh, did I miss this little part here? Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 13, these 3 are 2. Yes, I missed this little part here. So this should be maybe like, I would say this is like 2/10. So this is let's say 13.3 instead of 13.1, right? 2/10. It's that little piece here. So 1/10 plus 2/10 is 0.3. So 13.3 times 20 is 266. Okay, so you can either utilize geometry and formulas, or you can simply make an approximation counting the number of squares. Each of these squares is 1 by 1, right? 1 meter squared. Therefore, we just count the number of squares, and then we multiply all that times the unit weight of the soil to get the weight of the slice. Okay, here's our slope again. Same kind of drawing, right? And down here I have listed the weights in kilonewton per meter into the page for the 6 slices, 15, 62, 86.8, etc. The next step is to determine the moment arm, or the moment arms. So if you recognize what's happening here, this wedge is essentially at the moment of failure beginning to slide on the failure surface, and the sliding is actually a rotational one about the center of the circle. So you can imagine that this is like a hammock, where the hammock is basically hanging from the center of the circle, and so this will rotate like this, clockwise, right? All right, so the moment arm for each slice is calculated, or it is the distance from the centroid of the slice to the point. Okay, so how does that work? Well, let's see what happens here. Slice number 1. Slice number 1 is a triangle, and therefore its centroid, it's located a third of the way up from the long side. So we said that this was 1.5. It's a third of the way up from here. And so we can draw an arrow to denote this weight, this 15 right here. This 15 is the weight of the slice, and it acts at the centroid, which is 1/3 of this distance from this point. So this right here is a third of 1.5, because this is 1.5 according to us, right? Now, what is the moment arm? Remember that the moment arm is the distance from the point in question to the point over here in question, that is where the force is acting, in this case the weight. But that distance has to be normal to the arrow that denotes the force. What is the distance from here to here with a line, measured with a line that is normal to this arrow? Well, we have to extend the arrow like this. And so the distance that is relevant is this one right here, from the point to the extension of the arrow, so that the distance is normal to the arrow. That's the moment arm for slice 1. So what is it? Well, the distance is a third of 1.5 plus 3 plus 0.4. A third of 1.5 is 0.5 plus 3, 3.5 plus 0.4, 3.9 meters. 3.9 meters. Now, what happens with this slice? This slice doesn't only have a kind of an odd shape, let's say, it's a trapezoid, but part of it is denser than the other part, right? This part has a unit weight of 20 and this part has a unit weight of 22. So to get the centroid, one would have to use more advanced, let's say, calculations, or more calculations than what I'm going to show you now. This is going to be very simple, again, because we are approximating. How do we determine where the centroid is? Well, we're going to do it this way. We're going to say that 20 and 22 kilonewton per meter cubed are pretty similar, and therefore we could say that this is a single material for the purpose of getting the moment arm only. And then what we're going to do is do this exercise. We're going to say that we're going to take scissors and cut this little slice out of the page, and we're going to balance it on the tip of the pencil, right? So we're going to say that we're going to find the centroid by determining the point on which the little piece of paper would remain balanced on the tip of a pencil if we were to do that experiment. So I would say that there's somewhere maybe around here, basically saying that this is the centroid. Then weight number 2 acts here, and what is the distance? 0.4 and then 2, but minus this little distance right here. So moment arm number 2 will be from here to here. So 0.4 plus 2 minus this distance. What is that distance? We're going to say that's, I don't know, 0.2. So from here to here, 1.8, and then this is 0.4. So this is 2.2. That is, the moment arm is 2.2. Okay, for slice number 3, I imagine the centroid would be maybe somewhere around here. So if I draw the arrow here, what would be the moment arm? Right? So this is a third, and this is 0.4. So 0.4 plus 0.33 is 0.73. Slice number 4 has this little triangle up here, but it's so long that we could say that basically the centroid is somewhere down the center of the shape. Okay? So what is the moment arm? We said that the width of this slice was 0.6, so half of it is 0.3. Notice that now the moment arm for slice number 4 is measured to the right of the center of the circle, which is this distance right there. By the same token, number 5, maybe somewhere here, right at the center, even though this part is denser, right? So what do we have here? What distance do we have here? .6 plus 1, 1.6 plus 0.5 is 2.1. And slice number 6, essentially, I would put it somewhere there. And so this is halfway between this point and this point. So what do we have? We have 0.6, 1, 2, 3, 4, plus 0.5. So 4.6 plus 0.5 is 5.1. What are the units of moment arm? Obviously, meters. It's just simply a distance. We have computed weights, the weight of each slice, and the moment arm associated with each slice. So now we're going to compute the moment associated with each of these slices. And it's very simple, simply the force times distance, the weight times the moment arm. So the weight times the moment arm is equal to the moment. 15 times 3.9, 58.5, etc., etc. You can press pause and write them down if you want. But importantly, let's look at the units. Force, kilonewton per meter of slice into the page. Moment arm, simply a distance, meters, right? If we multiply this times this, we get kilonewton per meter times meter. Up here is the unit that you know of a moment, kilonewton times meter. So this moment is kilonewton, or has units of kilonewton meter per meter of slice into the page, right? Remember, to the problem. Now, there is something that we have to talk about here that is very, very important. Notice that this slice number 1, this slice number 2, and this slice number 3 are to the left of the center of the circle. That is, to the left of this line that we drew initially. So if we were to remove 1, 2, and 3, if we were to remove these slices, then slices 4, 5, and 6 would slide to the left, right? Now, what would happen if we remove 4, 5, and 6, but we leave 1, 2, and 3? If we do that, number 1, 2, and 3 will slide to the right. So the geometry of this problem and the circle that we drew reveal the following. Slice 1, slice 2, and slice 3 are actually resisting slices. They're there to help prevent the movement of 4, 5, and 6. These are the driving slices. Why? Because if you remove the resisting ones, these ones, the driving ones, will fall in the direction of the anticipated landslide, which is to the left, right? Okay, what does that mean in terms of the numbers? That means that we have to assign negative values to the slices 1, 2, and 3 because they are resisting. Okay? Here is our slope again, and we have to recognize something right here. We know that there's 3 slices that are resisting, 1, 2, and 3 are resisting the failure, right? They're resisting the movement of 4, 5, and 6. So that's good. But there's also an additional component of resistance, which is the strength along the failure surface, as we had described earlier. Actually, like this. Now, how do we capture that and input it or place it inside the factor safety equation, which is what we're trying to find, right? The factor safety for this wedge. Well, the way we do it is first by recognizing that the failure surface passes through 2 soils. Over here, it passes through soil 1. Over here, it passes through soil 2. And over here, it passes through soil 1 again. So we have to divide the failure surface into 3 parts in this case, because we have 1, 2, and 3 different parts of it. This is one part, this is another, and this is another. So when I draw these lines here, very roughly, sorry about that, I should have used a ruler. What I'm trying to do is the following. I'm trying to say, look, this portion of the failure surface is described by this angle, theta 1. This portion of the failure surface, which is on soil number 2, is defined by this angle, theta 2. And this portion of the failure surface is described by this angle, theta 3. So now we're going to use these angles to quantify the component of strength, soil strength, that is associated with each of the parts of the failure surface. Part 1, part 2, and part 3 in this case. Okay, here's a better drawn system. Here's our slope and our 3 angles, theta 1, theta 2, and theta 3. Now, what we do is we use a protractor to measure each of these angles. This first one, for example, is 15 degrees. The second one is 58 degrees. And number 3 is 60 degrees. These angles are used to determine the arc length of each of these components. The 15 is used for this arc length, the 58 degrees is used for this arc length, soil number 2, and the 60 is used for this arc length, soil number 1 again. Soil 1, soil 1, soil 2. So then very simply what we do is the following. We create a column called SU theta. And this is simply the SU of the soil in question times the angle, right? So what is the strength of the first soil? The strength is 100 kPa and the theta is 15 kPa, right? And this is in degrees. 100 times 15, that's this component right there. The second component, the strength of that soil, is 80 kPa and the angle is 58. And then the third one, the third component of the failure surface is this one right here, soil number 1 again. So it is 100 kPa and the angle is 60. The multiplications yield the following. Clearly 1500, 6000, and this is 4640. Now the units are kind of weird, right? kPa times degrees. But what's going to happen here is that we're going to place this inside the factor safety equation, and this multiplication is going to essentially be part of the calculation of the force associated with each of these components. For example, this one, the force associated with the resistance, that is the strength, would basically be drawn like that. And that force times the moment arm I'm using this particular one as an example, but there would be 3 of these, right? This particular one as an example, the moment arm is normal to the arrow that denotes the force which comes from the strength component. Remember, the strength is a tau. So the tau is converted to a force and through an area, and then the force is multiplied times the moment arm, which is the radius of the circle, which can be determined and measured with a ruler, right? But we're going to do it in a second. And that essentially produces the moment that is associated with the resistance along this particular portion of the failure surface. Again, there's another one here, right? We can denote it like that. That's a force that comes from the strength of this soil and an area. That is the area defined by the arc length and 1 meter into the page. That is the force. And then this is the moment arm. And of course here we have another one. And so the factor of safety is written as follows: pi r squared divided by 180. Notice that the pi over 180 is the conversion factor that one uses to go from degrees to radians, right? And one of these r's is this r here, which is the moment arm for each of these 3 components of the failure surface. Okay? And here we have the sum of the SU thetas, and down here the sum of the moments. This summation is 12,140. So this is that. Sum of moments. Here are our moments. If we sum them, 1,751.2. Notice that we're summing positive numbers and also negative numbers. Negative 58.5 plus negative 136.4 plus negative, etc. Plus 16.6, etc. So that belongs here. 1751.2 kilonewton meter per meter, right? Okay, so what's the radius? We can look at it here. The radius is 0.6, 1, 2, 3, 4, 5, 6. We could say that this is also 0.6. So 1, 2, 3, 4, 5, 6 plus 1.2 is 7.2 meters. So the factor of safety is calculated as 6.3. Clearly, this is larger than 1, so this is not a failure. And we could say that it's larger than, let's say, 2. Larger than 2 means that basically we have a safe slope. Now, do we have a safe slope? Do we just proceed with anything else that we're doing? No, because you have to recognize that this failure surface that we evaluated is just one of a universe of them. There are infinity of them that we can analyze, and this one is not necessarily the critical one. This is simply one of the infinity of them that we could analyze. So what we do is we tell the computer to draw, let's say, 1,000 or even 10,000 failure surfaces. So we tell the computer, vary the size of the circle and vary the location where the center is, near the vicinity of the slope, for example. And then calculate the factor of safety for all of them, all 10,000 of them, for example. And then tell me which one has the smallest factor of safety, and I will call that the critical one. If that factor of safety is more than 1, then the slope is not at failure, that's good. And if the factor of safety that is critical is larger than 2, then we say that that's a safe slope. I mean, this is totally true. This is just a reasonable approximation of what we do in the field.